All right, hi, your tens, this is Mr. Lim here again, and this is a video to help you with work and energy, just to catch you up because we're running out of time in class, so let's get started. All right, so let's have a look. So this is a new definition of what we mean by work, so let's have a look. Work is a measurement of the energy used to move an object over a particular distance or displacement. So unit is a measure of energy, right? So if you move something, you require a force to do so. And then depending on how far you move it, it will take a certain amount of energy to do so, right? So work is equal to the force that you use, times the distance that you push it. Okay, so force times the distance, right? And then we have a couple of fairly basic examples to go through. So a man is pushing his car along a flat road because he ran out of petrol. If it requires 900 newtons of force to push, how much work will he have done if he pushes it 500 meters? So let's have a go at that. Let's make that just right. Okay, cool. So he's going to have done, let's have a look. So it's asking for how much work will he have done, so we need the work equation. Now remember, you should always write out the equations that you're going to be using, right? So work is equal to Fs. We're going to substitute in these values. F is equal to 900, and S is equal to 900, and 500 is how far he pushes it, all right? And that equals 450,000 joules. Okay, so the unit for work, which is effectively a measure of energy, is joules, right? So work is equal to Fs. All right, also, if you are also not sure about everything, you can also just write out what you're solving. So force is equal to 900, distance is equal to 500, and then you can substitute that into your equation when you need to, all right? So after using up 240,000 joules of energy, the man gives up and takes a rest. How far did he push the car before he got tired? So he uses up a certain amount of energy. That's the work that he's done. So the work is equal to 240,000 joules. Okay, that's how much work he put in before he gave up. He was pushing with a force of 900 newtons, right? And so how far will he have gone before he gives up? All right, so we can rearrange that equation. Work is equal to Fs, or S is equal to work over F. Okay, you can write out the triangle here, WFS. Okay, so if you're looking for S, then you will have W over F. We substitute in those values, 240,000 over 900, which happens to equal 266.67 meters. All right, so list out what you know, write out the equation, rearrange the equation if you need to, and then do the calculation. Let's read the next bit. He then proceeds to use up 20,000 joules to push the car another 100 meters. How much force is being applied to the car? So again, the work or the energy that he's used up is 20,000 joules, so much less than what he was using before. How far has he gone? 100 meters. And we want to know what force is he pushing with. So we have to use that equation. Let's do that again. W is equal to Fs. Rearrange that equation. F is equal to W over S. Okay, and then you will have the work 20,000 over 100, which happens to be equal to 200 newtons. Okay, so he's pushing with a lot less force, right? Maybe he's found a buddy to help him push, but he's pushing with a lot less force. That's why he can use much less energy. Right, let's have a look at the next slide. Okay, so this is the triangle that you can use, okay? And these are the variations of that. These here are the variations of that equation. I would write it as F is equal to W over S, or S is equal to W over F. All right, but if you remember this triangle, or if you can remember it from that one there, then you will be able to rearrange that equation. Okay, so energy is that ability to do work. So work and energy are sometimes interchangeable, but energy can also be stored instead of actually being used to do something. All right, so energy is the ability to do work rather than work being done. Two main forms of energy involved in the motion of objects is kinetic and gravitational potential energy. So here, this dude over here with the ball, it's got potential energy. It has the ability to do work as it falls down. So as the person drops it, it turns into kinetic energy as it moves faster. And because it's lower off the ground, it's got less potential to do work. So effectively, the potential energy is transforming into kinetic energy, right? So high potential energy, medium potential energy, and then when it hits the ground, it's got zero potential energy, and it's got lots of kinetic energy, right? So energy in motion or energy from how high you are off the ground. Let's have a look at this first type of energy, kinetic energy, right? The energy associated with movement. So it depends on the mass and the speed or velocity of an object. Okay, so mass is this m here, and the velocity is this over here. So EK is or kinetic energy is equal to half m times m times v squared. Okay, so that's v squared, not square of everything. Okay, the units for these things are masses in kilograms, speed velocity is in meters per second, and the kinetic energy is in joules. So if you will recognize this kinetic energy is the same unit as work, because work is the use of energy or the doing of stuff with energy, right? This is kinetic energy here. Look at the rearrangement of the equation. If you're trying to solve for the mass of something, you can do 2 times the kinetic energy, and I might write it out like this. Oops, that's not what I want. Mass is equal to 2 times EK over V squared, okay? Or alternatively, V, and this is much more an important thing, is equal to the square root of 2 times EK over the mass, right? That's just a rearrangement. That K really should be a small k. But let's have a look at some of the equations here that we've got, right? So let's do this one here, okay? A 1,200 kilogram car has 400,000 joules of energy. Determine the speed of the car. So we want the speed of the car. So we're looking to rearrange, or let's work out what we've got first. We've got the mass, 1,200 kilograms. We've got the EK, the energy, which is 400,000 joules. We want to have the V, that is our unknown. Okay, so we can use EK is equal to half m times V squared. And the rearrangement of this equation is V is equal to the square root of EK times 2 over m, right? Now, when I do this calculation, I'm going to show you how you should do it on your calculator in theory as well. Because you've got to do this in part by part by part, because you can't do this all at once unless you're an expert with brackets, okay? So if you're an expert with brackets, go ahead and do this all at one hit, but I would suggest that you do this part by part by part, and then it will make it a little bit easier if you're doing this for the first time. So let's go put in some values. EK is equal to 400,000 times that by 2 over 1,200 square root. So the first thing that you should do on your calculator is this part here. This part here, the 400,000 times 2, right? So that will be equal to 800,000. So in your calculator, you would do 400,000 times 2, okay? Then press equals. Then you would do, okay, the next part of it would be the 800,000 divided by 1,200. So it's effectively this bit here, the 800,000 divided by the 1,200, okay? So that would be the square root then of 800,000 divided by 1,200, which would be 666.67, okay? So you would just done those two steps, and then you would press equals again, and then you would find the square root button, and if you're not sure where that square root button is, you go find that on your calculator, or Mr. Lim will help you find it, and you square root that value, and you can use the square root answer function, and you'll get the 25.8 meters per second as your value. Right, so that's the first one there. So I would suggest you do this bit first, then you do that number divided by that, and then you do the square root function. Unless you're a pro at brackets, and then you can do it all at once. Right, so let's have a look here. The same car then picks up 2 passengers, adding 130 kilograms to the mass of the car. If it is traveling at the same speed as in the last question, how much energy does it have? Okay, so first of all, the mass of the car is now equal to 1,200 plus 130, which is equal to 1,330 kilograms, because it picked up 2 passengers, right? It's traveling at the same speed as the last one, which was, if my memory serves me, 25.8 meters per second, right? So 25.8 meters per second. And I want the energy that it has. Okay, so remember, you just got to list out all the things that you know which will help you. All right, now we go EK is equal to half mv squared. So half times 1,300 times 25.8 squared. If you remember your BIMDAS rules, you should do the squaring first, right? So you should do, well, you should technically do brackets first, but yeah, everything in the brackets first, but the squaring is within the brackets, and this should be in brackets. All right, so 1,330 times that squared, which happens to be 666.67, then times that by the 1,330, you'll get 88666.67. Okay, so what I'm saying is that when you do this on the calculator, you do this first, and then you press equals. Then you do this, then press equals. Then you divide it by 2, and then press equals, and you will get a value of 44333.3 joules. That's how much energy that it has. Right? So, next question, right? The car with the 2 passengers now must slow down for roadworks. If it travels at 20 kilometers per hour, determine the amount of energy it has. So, again, car with 2 people, so the mass is 1,300 kilograms. The speed at which they're traveling at is 20 kilometers per hour, but we need this in meters per second. So that equals 20 times, divide by, because to convert this into meters per second, you divide by 3.6, and that gets you 5.56 meters per second, right? So converting between kilometers per hour and meters per second is something that we did last term, or a couple of terms ago, but you still need to remember it, okay? And then your EK is your unknown. Okay, so let's have a look here. So we've got that there, so we can go start putting it into the equation. So EK is equal to half mv squared, right? So half times 1,330 times v squared, which is 5.56 squared. I do the 5.56 squared first in my calculator, and I'll just do 5.56 squared, and it will be 30.86. So I'll press the equals button after the squared, times that by the 1,330, and I'll get 4, and press n equals, and I'll get 4149.4, and then I halve that, and once I halve that, I will get 20524.7 joules. Okay, so that is the amount of energy that one has. Because it's going much slower, the amount of energy is much lower. Right, let's move on. Oh wait, there's more questions here. Okay, so let's have a look at this one here. Okay, a 30-gram bullet is fired from a gun with 20,000 joules of energy. Determine the speed of the bullet as it exits the gun. Again, write out what I know. The mass is 0.03 kilograms. So you've got to convert from grams to kilograms, okay, because that's the SI unit, right? The energy, EK, is equal to 20,000 joules, and I don't know what the velocity is. So V is equal to the square root of EK times 2 over M. and the whole square root of that. So I would substitute values in, 20,000 times 2 over 0.03, square root all of that. Okay, which parts do you do first? You do that bit first, then you divide that number by this, and then you square root it, and the value will be, you should work it out yourself, and once you've done that, you should check it against this value here. Right, let's have a look at the next question. Right, air resistance applies a force on the bullet of 15 newtons. If the bullet travels 600 meters, how much work was done by the air? So this question is asking about work. So work, unknown. Force, because that's what work is, the equation for thing, right, is 15. How far? 600 meters. And that's 15 newtons. So what's the work done? Work is Fs, right? So 15 times 600, which is equal to 9,000 joules. Now, what work has the air done on the bullet? It has effectively slowed it down. So it now has more or less kinetic energy. It has less kinetic energy, right? So now when we say, what is the speed of the bullet at the end of the 600 meters, we will say that, okay, then, the kinetic energy that it has after 600 meters is the initial amount of energy that it has, which was 20,000. Subtract the 9,000 that was taken from the air resistance. So this is initial, and this is from air resistance, taking away some of the energy. And so therefore, it's only got 11,000 joules of energy. Okay, its mass remains the same, right? 0.03 kilograms. Okay, but now we have to work out its new velocity with these new things. Okay, so the velocity will then equal the square root of EK times 2 divided by m, which will be equal to 11,000 times 2 divided by 0.03, all square rooted. Okay, and that will equal, what's that value? 856.3 meters per second. All right? All right, the other type of energy is gravitational potential energy, which is the energy associated when the body is lifted above the ground and the height changes. Right? So it's dependent on the mass and the height of the object, and as well as the planet that you're on. All right, but we're all on here, so that doesn't make a difference. All right, so M is for mass, G is for the gravitational acceleration, and H is for the height above the ground, okay? Now, technically that height is the height above whatever the lowest point you can get to, but generally it'll be nice and clear in the question what kind of heights you're talking about. All right, so the potential energy is equal to mass times gravity times the height. Okay, you can rearrange the equation to get different versions of them, like this. All right, the last one would be G is equal to what? EP over MH. Right, if you wanted to do that one there. But let's have a look at some questions. Okay, so an eagle weighing 3.4 kilograms is flying 200 meters in the air. Determine the amount of gravitational potential energy it has. Right, so let's have a think. What do we know? Okay, so we know the mass of the eagle is 3.4 kilograms. We know that its height is 200 meters in the air. We want to work out its gravitational potential energy, right? And we know that it's on Earth, which means that it has a G value of 9.8, right? So this G value of 9.8 is going to be consistent all across the Earth, and in the test and in questions and in the data sheet, it will tell you 9.8, and that's the value you have to use, right? So we can put that into the equation. So write out the equation, write out the things that you know, substitute in the values, and you'll get a certain value, 6664 joules, okay? Because this is the amount of energy it has, that's the amount of work that it can possibly do, right? Let's have a look down here. So Now it says that it swoops down so that it only has 3,000 joules of energy, gravitational potential energy. Determine that the height that it is now soaring at. So we know its mass is 3.4 kilograms from before. We now know that it is only got 3,000 joules of energy. And we know that gravity is 9.8, but we're not sure about how high it is off the ground. Okay, so how high is it off the ground? Let's work that out. EP is equal to mgh, which means that h is equal to EP over mg. Okay, so 3,000 over m times g. Please, when you do this in your calculator, either do this step first and then do 3,000 divided by that number, or put brackets around this, because if you do not put this number in brackets, you'll do 3,000 divided by 3.4 times 9.8, which will get you a very different value. So please put brackets around those there, otherwise your calculator is going to give you something odd, right? And you should get, it is at 90 meters, right? Lastly, an alien abducts an eagle and teleports it to the moon, where it now only has 1,090 joules of energy as it suffocates at 200 meters above the moon's surface. Right, determine the gravitational field strength of the moon. So now we have the mass of the object, 3.4 kilograms. We have the energy that it has, 1090 joules. We have its height at 200 meters. Right, and we're trying to find out what the gravitational field strength at the moon is. Right, so we're going to rearrange this equation. EP is equal to mgh, so G is equal to EP over mh. So 1090 over 3.4 times 200, which happens to be 1.6. And this is the acceleration due to gravity at the moon, so it's meters per second. Right, but they also have other units as well. Right, so let's move on. All right, the last bit is the law of conservation of energy, which states that energy cannot be created or destroyed. Right, so similar to mass, it's not created or destroyed. It can only be transferred, which moves from one object to another, or it can be transformed, which means it changes from one form to another. Right, so this idea that the energies that we've been dealing with, the kinetic and the gravitational potential energy, they're changing from one to another. So say what happens if I get a ball and I hold it in my hands, then I throw it up. All right, I throw up the ball. Okay, when I throw it, it's going to go very fast at the bottom. All right, so I throw it up, it's going fast at the bottom. It's going to slow down as it rises up, and then it's going to stop at the top. So fast here, when it's going fast at my hand, it has high EK. Then it has less EK as it slows down because its kinetic energy is going down. And then it has no EK. Oops. No EK at the top because it's stopped. Right? It's stopped. Okay? So, where has that energy gone? It's not as if that energy can just disappear. So, at the top, it has a high amount of EP, or gravitational potential energy. Right? As it goes up, it gets... as it's going up, it has a little EP, and then it has a low EP at the bottom, right? Why does it have low EP at the bottom and not have zero gravitational potential energy? Well, when I was holding it off the ground, so it still has the gravitational potential energy from here to here, right? So it doesn't have no gravitational potential energy if you're holding it, but if it's on the ground, it would have no gravitational potential energy. All right, so the idea is that if you were to graph this over time, right, the kinetic energy would start out high and then go down, and the gravitational potential energy would go up here, right? But well, I think we're going to go through another idea in a moment, right? So let's go look at that next idea. Then, because you're converting gravitational potential energy to kinetic energy, we have this idea of both of those two things put together is what's known as total mechanical energy. Okay, mechanical energy, I don't know why it's called mechanical energy. It's just a combination of potential and kinetic energy. All right, so the amount of energy that it has in total is the mechanical energy. And it's how much potential energy it has and how much kinetic energy it has. All right, so let's this example over here with the some dude on a skateboard or ice snowboarder or something like that. All right, so at the top, he's stopped and he has 0 kinetic energy because he's not moving. However, because he's so high off the ground, he has a ton of potential energy. All right. As he slides down, that potential energy turns into kinetic energy. Right. And now, halfway down the hill, he's got a ton of kinetic energy and still quite a lot of potential energy. All right. At the bottom of the dip here, it's got a lot of kinetic energy, but not so much potential energy. Right. Still got some because he's not on the ground yet. Then, as he goes up here, have a think, is the kinetic energy going to get higher or lower? It's going to get lower between here and here because he's going to slow down as he goes up that ramp. Right? What's going to happen to his potential energy? That's going to go up because he's going up this amount of distance. Right? And he's going to keep on going up as he goes up to the maximum height of his jump, and he's going to go back to the same level that he was before over here, right? And if they're at the same height, they're going to have the same amount of potential energy and the same amount of kinetic energy, assuming that there's no friction, right? Then he's going to fall down, going to get faster, 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 and then he's going to hit the dirt and slide away coolly. All right, so that's when he's got the most amount of kinetic energy and the least amount of potential energy. Right? So the idea is that it converts and it goes up and down depending on how that goes. And I think that was in the style lesson. All right? So let's have a look at this dude here. First of all, can we work out the height that this dude is at the beginning? Right? So let's just say that, okay, his mass is 50 kilos. Mass is 50 kilos. Right? His height, unknown. His EP, or potential energy, is equal to 50,000 joules. And he's on Earth. He's got 9.8 gravity. All right. So H is equal to EP over M times G. Remember to put that in brackets. So that will be 50,000 over bracket 50 times 9.8, which will be equal to some value very close to 100. Okay, 50 times 9.8. And he's at 102.0 meters. Right. This value is actually 100 meters because they're using 10 instead of 9.8 for that one there. But doesn't matter. All right. So that's the idea. He's got a lot of potential energy at the top. Then he's going to start sliding down. Right. As he builds up speed, he can work out his kinetic energy is going up and his potential energy is going down. But we can work out how fast he's going even. Right. So if we can work out how fast he's going, right, so we can say that, okay, what is his mass? 50 kilos. What is his EK? At that point, at number 2, it is 20,000. Right. So we are looking for the velocity. Okay, so V is equal to the square root of EK over, or times 2, over M. Right. So you got to do that in your calculator. Make sure that you do it part by part. So 20,000 times 2 equals 40,000. Divided by 50 equals 800. Square root that answer, and you get 28.28 meters per second. That's how fast he's going there, right? He's going to get even faster as he goes down, right? He's going to get even faster as he goes down to stage 3, right, where he will have 35,000 kilojoules of energy. Then he's going to go back up to number 4 over here, right, where he's going to be going at the exact same speed because he's got the exact same kilojoules, right, or joules of kinetic energy, and then he's going to go at the bottom there, right? So let's have a look at the bottom. Let's see how fast he's going, right? So if I say that his mass is still 50 kilos, his EK is now 50,000, all of his energy is turned into kinetic energy, right? We don't know what the V is, so V is equal to the square root of 50,000 times 2 over 50, all right, which will be equal to some value, so 50,000 times 2 divided by 50 equals 2,000. Square root that answer, and you get 44.7 meters per second. So he's going much faster than he was before, right? So let's have a look at some questions here. We might just go through some of these more wordy ones, and let's have a look here. The diagram shows 5 points on a roller coaster. List the points in order from the point where the car would have the greatest potential energy, so the highest potential energy, to where it would have the lowest potential energy. Okay, so the highest potential energy is the point where he is highest. Okay, so where is he the highest? He's highest at A, then at E, then at B, then at D, then at C. Okay, so you go from highest to lowest. Now you want to have the list the points in order of the greatest kinetic energy to the least amount of kinetic energy. So the idea would then be, okay, where is he going the slowest? Oh, wait, you want the fastest? The fastest would be where he is the lowest. So C, then D, then B, then E, then A. Right, so effectively the reverse order, because remember, at any given point in time, the potential and the potential energy and the kinetic energy are going to add up to the same. Right, they're opposites. All right, okay, so there was a concept map there, but I got rid of it. All right, okay, so let's have a look here. A 74 kilogram student starting at rest slides down a 11 meter high water slide. How fast is he going at the bottom of the slide? So, a couple of things here. I know my mass, 74. I know my height, 11.8. Right, is that all the information that he's got? Right, but you actually need to work out the V. But there's a couple of steps to this here. So we only have enough information to work out, well, we have also got G because we've always got G at 9.8. We've got enough information to work out his potential energy at the top of the slide as mgh, which is 74 times 9.8 times 11.8. That will be how much energy he has at the top of the slide, which will be 8557.36 joules. That's how much energy he has, right? So now that we have EK, we now have, because in theory, when he goes to the bottom of the slide, all of his potential energy is turned into kinetic energy. He now will have 8,557.36 joules of energy. His mass won't change, 74. And so therefore we can work out his velocity. So now we do V is equal to the square root of 8557.36 times 2 over 74, which happens to be, so 8557.36 times 2 is equal to 17114.72. Divide that by 74, 231.28. Then I square root that value, and I get 15.2 meters per second. Right. Let's have a look at number 11, and this will be the last one. So, determine the mechanical energy of a 450 kilogram roller coaster moving at 30 meters per second at the bottom of the first dip, which is 15 meters above the ground. So this is asking for the total mechanical energy, which is the potential plus the kinetic. So let's work out what things we know. The mass we know is 450. We know that it's moving at 30 meters per second. And we know that the first dip is equal to 15 meters above the ground. And we know that G is 9.8 because we always know that G is 9.8. Okay, so let's work out the kinetic energy first. The kinetic energy first will be equal to half mv squared, which will be equal to half outside of 450 times 30 squared, which will be equal to, so part you should do first is the 30 squared. 30 squared is equal to 900. Times that by 450 is 405,000. Divide that by 2, and that is 202,500 joules. So that's his kinetic energy. Now let's work out his potential energy. It's mgh. What's that? M is 74. No, wait. M is 450, because now we're doing the roller coaster. Times G, 9.8, times H, 15. So 450 plus 9.8 plus 15 is 474.8 joules. Then the total mechanical energy is equal to the EK plus the EP, and that'll be equal to some value, 202,974.8 joules. Right. So that's that. If you have any questions, come and see us, but we're running a bit short on time, so come see us soon. Adios.